we're going to talk about rational functions. We've been adding basic functions to our list. Let's say basic functions so far. We have our quadratic function, all our polynomials, x cubed, x to the 4. Now technically you can keep going, x to the 5 and so on, but because x to the 5, 7, 9, 11 and all those look basically and behave very similar to x cubed, we don't really bother mixing them up too much. Same for all the even powers, x to the 4, x to the 6, and so on. So we really only have these three different ones. And then also we have y equals square root of x. So for all of these, the polynomials all have the feature that we can plug in any value of x. The square root function was a little different in that it wasn't defined for all the x values, and because of that, having a negative sign inside, we had to introduce a new horizontal reflection transformation. Now we're going to add one more, and it's going to be y equals 1 over x, with properties that the others don't capture. Here I can plug in pretty much everything except x equal to 0. And other interesting things happen in this kind of function, leading us to the rest of that chapter 1. Now we'll start by just saying these things in words, and then we'll refine the language and how we say it. First of all, I have two kinds of issues. I have what we'll call long-term behavior. That's also called asymptotic behavior. That's one. Well, asymptotic behavior is really called covering both. Long and, let's say, short-term extreme behavior. These are names I'm making up. There could be similar extreme things happening in the short term, and I'm not meaning a y-intercept. I'm meaning there's a problem. Let's do the second one first. If x gets closer to 0, then we can say something about the corresponding behavior of the y values, and therefore the function, and the graph, and all those things. What happens when x gets smaller and smaller and smaller in size, closer to 0? What happens to the y value? So in other words, what happens to the calculation 1 over x? Well, let's put in some numbers to see. And that might help some people. Let's try some x values and then get some y values. We're making them smaller, right? So let's go with 1. Ooh, that's not a horizontal line at all. Let's say 0.1, 0.01, 0.001, and you can keep going, of course. But that should be enough. When x is equal to 1, y is equal to 1, okay, fine. Not very small. In the grand scheme of things, 1 is actually quite big. When x is 0.1, y is equal to what? Get a whole snow day to relax and do all kinds of problems, catch up. What is y equal to? 10. When x is 0.01, 100, 0.001, 1,000, and I can just keep going. But I see that as x gets closer to 0, the y value blows up in size. And the smaller my x value becomes, the bigger my y value is going to become. Let's just say here gets bigger. But different things are going to happen if my x value is still behaving like this, but always positive versus always negative. Always positive, then great. The y value is going to be a positive number. But if x is always negative, it's still getting smaller in size, but the y value is now also going to be negative. So different things are happening depending on how I approach this 0x value. Do I come at it from the right? Do I come at it from the left? Different things are happening to this function. So I need to specify if x gets closer to 0 from the right, meaning from the positive side, then x gets bigger, positive. Meaning that as I'm walking towards the y-axis, my graph is going to curve up. And it can never get to touch the y-axis. The y values just get bigger and bigger and bigger the closer I get. But I'll write it over here. If x gets closer to 0 from the left, meaning negative, then y gets, I'll say, bigger in size, but negative. I want to use words that distinguish between the size and the sign. So the size of the y values are big. It could be positive or negative. So I'll say big negative, because small means close to 0. So as I come at this x equal to 0 point, I can't get there because I can't plug that number in. But I can get really close, and then I'm going to go down because that's where the negative y values get bigger and bigger in size. Okay? Everyone happy with these two sentences at the bottom? Different things are happening from different sides. Any questions on those two sentences? Those two sentences are going to come up a whole bunch in different forms, but still the same sentence. So that's one aspect. Sort of in the short term, x has a finite value where if I approach it, strange things, extreme things happen. Okay. But I also want to know what happens if I go far to the right, far to the left, the long-term behavior. So I'll do this next, this bottom one, or this top one at the bottom. So there are two more questions. As x gets bigger, positive, that's how I'll say it, y does what? Well, I look at my function, zoom out a little. There's my function over there, 1 over x. You can make a table to convince yourself. If I take bigger and bigger positive x values, what happens to 1 over x? Yes? It's going to get smaller and smaller. Y gets smaller, positive or negative? Well, x is always positive, so y is going to be positive as well. That tells me if I go far to the right on this graph along the x-axis, my graph is going to have smaller and smaller y values, never getting to 0. I can't get 0. I can get something extremely small, but it will never actually be 0. It will always be a little positive number. And the next sentence, as x gets bigger in size but negative, I don't want to say smaller here because that means close to 0. Bigger in size but negative, y again gets smaller, meaning closer to 0, but negative. So as I go far to the left, my y value is going to stay negative, but get smaller and smaller in size. So I have properties in this basic function that do not feature in the previous ones. And I can update these arrows, erase, to make a smoother graph. Just sort of connecting these two. As smooth as you can. They never touch the axes, but they get really close. My surface is a little bumpy, nice and smooth. And for example, there's a reference point if you ever needed 1, 1, negative 1, 1, negative 1. So there's my graph. Oops. I keep showing the root x function. All right. So there's my basic function and some key properties that are sort of extreme in comparison to previous things we've seen. No x-intercept, no y-intercept, but I have these asymptotic behavior properties. I'll see if I can squeeze it in. Why not? So if we look at what happens when x gets close to 0, or a number, if the y value blows up in size, then we say the function, where should we say it? Oh, let's say it at the bottom. Let's not try and squeeze things in. We say the line, which is the y-axis, which is the line where the y-axis sits, which has equation x equal to 0, vertical straight line, is a vertical asymptote. That is an O. O. And the x-axis is also a straight line that the graph approaches, but never touches, never crosses in the long term. So we say that line, which has equation y equal to 0, is a horizontal asymptote. These extreme things that the graph approach, they approach both one at a time. The vertical asymptote, the graph approaches as I get close to a specific x value, the y value just blows up, and it can never get through that line. Vertical asymptote. Horizontal asymptote, the extreme long-term behavior, far to the right, when all is said and done, does it stabilize and get closer and closer to some straight line, some horizontal straight line? To the right, to the left? If it does, that is called a horizontal asymptote. And we'll refine these things as we go, but for now, saying everything in words will be sufficient. Any questions so far? Some of these things may be familiar. Sometimes the way we want to write them might not be familiar, though the concept is. Sometimes it's all brand new. We'll slowly transition to newer and newer things. Okay, but first, actually, let's maybe... Next, we have a basic function. Let's put a pin in this asymptotic behavior stuff. And let's just see, well, we have a basic function, this y equals 1 over x. We should probably do some transformations on that before moving on. So let's see. What that would look like. Now, I don't think in the book I have both versions of the question, which is totally fine. Oh, no, I do. Very nice. Problem 111. Number 6. I have y equals 1 minus 3 over x. Now it becomes less obvious what the transformations are. I don't have brackets. I don't have a square root, which sort of looks like some bracket containing something to illustrate and highlight the transformations. But I can still make my sequence of transformations starting with y equals 1 over x. I'm just going to focus on the sequence of transformations because once I see in isolation what they are, doing the corresponding thing to the graph is pretty straightforward. So in the interest of saving time, I'm not going to graph everything, but you should always be able to graph it. Next, I'm going to multiply the right-hand side with negative 1. If I do that, what happens to the previous graph? So we'll just talk about graphically what happens. And you can slowly make sure you can actually draw that. What happens to the graph if that is my function transformation? It's flipped vertically. Next, I will multiply the whole right-hand side with 3, and that will give me the 3 over x that I need. Multiplying the whole right-hand side by 3. Now, of course, you could write this as negative 3 times 1 over x, but they're all equivalent. So it's a little more hidden, perhaps, because the number isn't clearly in front, but whatever. If I multiply the whole right-hand side by 3, then everything stretches by 3. And lastly, so I could have seen this as negative 3 times 1 over x plus 1. Then the transformations are more clearly visible. One way or another, I can get to the final function by adding 1. Maybe we should do this one. Just 1 at least. Yeah. And then that is going to result in a vertical shift. I'll do it quickly. So 1 is at least done. Ooh, I'm not going to have space for all these. Really small. Let's make them tiny graphs. Tiny graphs. But I'll zoom in so they're actually perfectly fine. There we go. I think we can do it. Y and x. Y and x. Y and x. Y and x. Okay, zoom in. Whoop, too much. So I have my basic shape. As long as you're sort of smooth and do not touch the x-axis or the y-axis, you are fine. I try and have a nice bend in them, not too straight, but it's not always the easiest thing. Now we're going to flip this vertically. So that means I'm going to have this shape after I flip it. That's a nice one to manipulate and transform. Try and not have those pieces too straight. They have actually a nice curve to them. Then I'm going to take that graph and stretch it a little bit. So in order for me to help show that I understand what to do, I'll keep track of a point. And one point will now be 1 and -1. So I don't want to draw a line that's too straight. That doesn't look that good. I'll rather focus on the shape and use my previous reference point to say, look, that is now at -3. I understand that all these things are stretched, but I adjusted the y-axis scale so that my shape still looks good. I can even do it for another point here. -1 and 1. That point there is now at -1, 3, whether it looks like it or not. And lastly, I shift everything up by 1, which means the horizontal asymptote that was sitting on the x-axis is now shifted up a little bit, sitting over there. And I can use that as a guide because I need to approach that asymptote. There are no y-intercepts to indicate, so I'm good. We just want a rough idea, because eventually we want to use these little graphs coming from a couple of transformations to help me with the actual question. The actual question eventually won't be to graph them in later tests, but understanding these little transformations and being able to visualize them either in your head or quickly sketching them makes a big difference in my comfort level with how functions behave and what they look like and their properties. I need to know those things. And later on, I'm going to ask you some things. What does this little graph look like? A couple of transformations in it, or maybe just one transformation. And every time, there's complete silence. No one knows what it looks like. Well, we've spent multiple hours on transformations so that you can know, so that that later portion of the course is easier. Any questions on transforming a 1 over x function?
So the last graph, that's asymptote of +1.
So in that case, the horizontal asymptote is, you can write that down, y equals 1. Let's write that down for sure. Because I shifted it vertically, the horizontal asymptote shifts with everything. It's a part of the graph. So I'll just say horizontal asymptote, y equal to 1. Maybe we should indicate the 1, you're right. Definitely. If there happened to be, in another example, a horizontal shift, then the vertical asymptote will be visible. And sometimes I get both. Now, in pre-calculus, you definitely did draw these guys, but perhaps not by way of transformations. And transformation is the thing that helps me a little bit in the future, more than anything else, to understand how the key properties have changed. So that's fine, but let's notice that if we take that previous function, 1 minus 3x, that's a nice form to have. If it's maybe a number, plus or minus some other number over x. And of course, there could have been x plus or minus 1 here as well. That could be the case as well, and we would have had to shift it horizontally. But if we simplify this, and notice other ways it could have looked, I can put it over a common denominator. Actually, let me make this worse. Let me put it this way. I know it's not the same as the original. This has a horizontal shift as well. But in more general cases, it'll have something like that. If I put it over a common denominator x minus 1, it's going to be x minus 1 over x minus 1, giving me the 1, minus 3 over x minus 1, giving me the second term. If I then simplify this, I get x minus 4 over x minus 1. Sort of, let's call this a more general form. The simplified versions are usually called the general form. And just like in the case of, well, not just like, similar to the case of the quadratic functions, I could have this general simplified form in a question, and I don't see the transformations immediately. Now, how we handle this is different from how we handle the quadratic function, because it's a completely different function, but the goal is the same. I need to make it look in a simpler way. I need to make it look better so I can see what the transformations are. That 4 is not any specific number of units that I shift or stretch or anything, because it's the simplified form. I can't read too much into these numbers. So how do we go backwards? Oops, that was a W. How to go back to a form where we see the transformations. Is everyone happy with the problem that we have when it's that simplified form? But if I tell you x minus 4 over x minus 1, how many transformations are there? I don't know. I can't see them. But in the original, 1 minus 3 over x minus 1, I can see them. The 1 is a vertical shift. The 3 is a stretch. The minus in front of it is a vertical reflection. The x minus 1 is a horizontal shift. Everything's fine. How do I get the general form to look like? It doesn't have a name. The transformation form, whatever you want to call it. How do I make it look like that so I can see what the transformations are from that basic one? The answer is long division. Now let me remember long division, because from the very first time that long division is introduced in elementary school, it really never had a fighting chance, because long is in the name. So any kid hearing the word, oh, we're going to learn long division, that's going to suck. It's long. I don't want to do it. It's just division. So let's take something simple like 7 over 2. Right? This is a fraction. And on the other side, we extend the long division to polynomial long division. But the principle is the same as for numbers. What I essentially want to do is write this as a mixed number. And this fraction is equivalent to division. The numbers don't have to be big. I say 2 goes into 7 3 times. 3 times 2 is 6. Take it away. I have 1 left. So that's my remainder, if you will. So here, another version of 7 over 2 is 3 and 1 half. So the quotient, the answer of the division is over there. Remainder on top of the original denominator. Long division. It's the same. But people think, oh, now I have x's, I need to do something completely different. No, it's almost exactly the same. Not exactly the same, because there are x's, but it's very similar. So, the 7 went inside the house, so the x minus 4 should go inside the house. And then the denominator is outside the house. But now, of course, it's not exactly the same because I don't have a number, I have an x. Still, the leading term is really the key aspect of that x minus 1. The minus 1 isn't as important as the x. So the only difference here with polynomial long division, and we're not going to make these super high powers of x or anything, is I'm only looking at the leading term. And if inside the house, if the numerator had more digits, I would still only look at the first part. So I'm only looking at the first part there. And then saying x goes into x once. And we'll see others as we go. 1 times the whole thing now. 1 times x minus 1 is x minus 1. So the only thing I have to remember is, for the initial little division, it's the leading terms that I compare. When I have that and I want to multiply before I can subtract, like 3 times 2 equals 6, I have to multiply with the whole x minus 1. And then I subtract all of that. X minus x is nothing. Negative 4 minus negative 1, that's negative 4 plus 1, that's negative 3. Now, the negative 3 doesn't have any x's, so x can't fit into it. So my remainder is negative 3. Giving me, I'm just going to erase this arrow because it's a little bit in my way, giving me the quote-unquote mixed number of, same thing, right? This answer to the division is sort of the whole portion. Now remember, in the 3.5, there's really a plus there, right? It's 3 plus a half. So there's really a plus there. The remainder over the denominator. And there you go. Now I can see all the transformations. Vertical shift of 1, negative in front of the 3 means a vertical reflection. The 3 means a vertical stretch. X minus 1, horizontal shift. How do you feel about long division? No one ever feels good about it. Just be honest with yourself. Don't say, oh no, I feel great, and then in the test and bad things happen because you were lying to yourself. That's the worst thing. We just need to practice this and see some variety. Still in problem 111, we now have some functions that we call rational functions whenever, I'll just do it as a side note here. Rational functions, that's when I have a fraction of functions. I have a numerator and a denominator, but they're both polynomials. Polynomial over polynomial. Now, yes, this is part of a much larger family. We're going to keep the polynomials nice and simple because we can only do transformations on basic ones. It is limited. Still, rational function. Which is why in the question they're asking me to graph the rational function with a transformation. Now let's build up to the difficult ones. Let's maybe do 7 first. Y equal to negative 2x plus 1 over x. I know long division isn't quite necessary there, but maybe it's an easier long division to get us used to that aspect. Because if I have 2 terms in the bottom, I don't have a choice. So I'm trying to see the transformations. Before I can apply the transformations and make the sequence and everything, I need to see the right version first. Now in general, long division will do that. I'm going to do it on the side here. So negative 2x plus 1 divided by x. I know it's not completely necessary, but that's the part we need to practice. So x goes into negative 2x, only the leading terms, negative 2 times. Negative 2 times all of this, which is just x, in this case, negative 2x. Take that away. So I get negative 2x plus 2x, and I have a 1 left. That's my remainder. So then this function can be rewritten as negative 2 plus 1 over x. And then I can make the transformations very easily. Start with 1 over x, there's not much to do there, and go to 1 over x minus 2. So just one transformation in that case. But looking at the original general form, negative 2x plus 1 over x, I wouldn't have guessed there's just one transformation. It did not feel like it. It felt like a lot more. The general form is very deceiving. I need to break it up to see the transformations. I can't go from the general form to the sequence of transformations. They're too hidden, I can't. So let's step it up a little bit to something a little more interesting, but to practice this long division. Because what if it's in the midterm? I need to be ready. Probably will be. Don't know. Very high chance. Let's go number 1. There I have x over 3x minus 6. How many transformations do you see? This is the one time where the answer I don't know is the appropriate answer. I have no idea. It's not in a form where I expect myself to see transformations. What does that 6 mean? No idea. Probably nothing. I need to see it. Long division is going to help me. The numerator is inside, the denominator is outside. What do I do next? It's the same as numbers, but not quite. It's a little bit more. What is the next thing in the long division story that I say? 3x into x, right? Outside into what's inside. And I get 1/3. Then 1/3 times the whole thing, which means 1/3 times 3x, which is x, supposed to be the same. But also 1/3 times negative 6, which is 2. Then subtract the whole thing. X minus x by design should be nothing. Nothing, 0, minus negative 2 is a 2. There are no x's here. Can't fit any more in, that's my remainder. Now because our polynomials are linear, it's not the full long division, but we don't need to see the full long division. This is what we need it for. So how do I rewrite this? I've done the long division, great, but it needs to tell me how to rewrite this rational function. Otherwise, it's pointless. What do I write first? 1/3, the answer, the quotient to the division. I'll always write a plus there. And then 2, the remainder over the original denominator, the divisor. It's not perfect. That's 3 in front of the x. Does that bother me? Should that bother me? No, shouldn't bother. I do need to clean it up. I need to take this out because I'm not interested in that transformation with numbers in front of the x. Not a big deal. X minus 2, when I factor it out, then this becomes 1/3 plus 2/3 over x minus 2. Now I see there are 3 transformations. none of them are using a 6. And none of them are really using a 3 in a direct way. I need to rewrite it, or I don't see the transformations, and I'm not expecting to see the transformations. Any thoughts or questions on that? Maybe slowly new things or less familiar things are coming. And when that happens, you need to step up your review accordingly, or nothing good will happen. Any questions on that? Do we need to do one more? Is it super easy? I don't want to waste your time. How do you feel? Yeah. So this is, let's do it, what's the easiest way to do it? I'll do it one way, you can tell me how you do. This is 3 over 1. So if I see that as a fraction, I'm dividing by 3 over 1. So I'm multiplying by 1 over 3. That's the same thing. And then I just group the 1 over 3 with the 2/3 because I don't know what to do with it next to the x. That helps at all.
Yeah, it does.
Okay. Different ways of seeing. Because in my list of transformations, trying to keep things as simple as possible, he asked that question as well a while back. I don't want to have a number in front of the x. I can always factor it out and put it somewhere else. Instead of seeing a new transformation, which is horizontally squishing things. That's bad news for me. Unless I'm working with trigonometric functions, I don't like that extra transformation when I don't need to. Let's do one more. I feel the need to do one more. Let's make it a lot of fun and do number 2. The snow is done. It's time to get serious. As new things are slowly creeping in. No, I'm not looking at the right function at all. Oh, I am. Aha. Very nice. There we go. Do I like the look of that as it is, moving to long division? Because if you don't stop and think at every step, you could very easily say, oh, well, I'm putting this inside the house, like he said, then I'm putting that side outside the house, then I'm comparing the first things, 5 goes into 3. No. The leading terms are what you compare. Meaning I want to maybe help myself and see the leading term first. Leading term first. Help yourself and always do the same thing. Have that consistency, give you confidence. Now, I compare the leading terms. Negative 2x goes into 7x, 7 or negative 7 over 2 times. And often these numbers aren't the nicest ones. Negative 7 over 2 times the whole thing times negative 2x. By design, I should get 7x. And negative 7 over 2 times 5, maybe I want to leave it as negative 35 over 2. Then subtract the whole thing. Fractions. Whether you love them or hate them, sometimes they're going to be there. And you just have to slow down, do not make a silly mistake. Everyone understands so far how we get that. Might need some practice. It's okay. There's more to practice. Now I'm taking it away, and the 7x's should cancel. I'm supposed to get something that is less in terms of the degree of the polynomial. 3, two negatives, plus 35 over 2. Well, 3 itself is 6 over 2. So 6 plus 35 over 2 is 41 over 2. Doesn't have to be pretty. And then that's my remainder. So that tells me that this seemingly simple rational function in the transformations has some unpleasant things to work with, the fractions. Negative 7 over 2 plus 41 over 2 divided by negative 2x plus 5. It's not great, but it is what it is. There's nothing I can do. You can will it to be other numbers, but it's not. And I'm also not done because there's a negative 2 in front of the x, which I do not like. So I will not skip any steps, so I'll just take that out as a factor. Then I have x minus 5 over 2. That negative 2 can go to the top to give me negative 41 over 4 all over x minus 5 over 2. So in the beginning, the general form of 3 plus 7x over 5 minus 2x, those numbers do combine to give me the transformations, but not in an obvious way. The actual transformations are vertical shift, yes, I do it at the end, but still, vertical shift down by 7 over 2, vertical reflection, a stretch by a factor of 4, vertical stretch by a factor of 41 over 4, horizontal shift by 5 over 2 to the right. Not pretty. But there's good news. In a test, if this is in the test, I will just ask you for the sequence of transformations, not the graph. Because graphing, shifting it with fractions, that gets a little annoying. So you still have to see what are the transformations, what is the sequence, but I trust that you can make the sequence from that yourself. Practice, practice, practice. If you need to, if these things aren't familiar as we go, and it's going to become less and less familiar, you need to adjust your studies accordingly.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.